Firstly, this study explores water leakage in Multiarch tunnel exposed to acidic groundwater using Monte-Carlo simulation and thermodynamic modeling. It identifies key leakages, reactions like carbon dioxide, carbon hydroxide, and organic matter, linking them well with observed data. The modeling approach is innovative, especially in handling complex tunnel structure. However, it's limited by a short-term focus, small simulation area, and lack of structural detail. To improve, future work should consider long-term durability, broader spatial coverage, and more precise structural parameters. Overall, the study provides valuable insights and contributes meaningful to tunnel waterproofing
So I'm
research.
going to talk about the background of the article that we have found. So the study shows about how acidic groundwater affects Multiarch tunnels in China. So this groundwater can damage tunnels by causing leaks and weakening waterproofing. So traditional studies look at the water and rock interactions either as purely mechanical or chemical, but not both together. So this study uses a Monte Carlo based nonlinear model, so it shows how these interactions happen in a random and changing way over time. This helps us better understand how leaks form in tunnels. So with this model, engineers can design stronger waterproofing and improve maintenance strategies to protect tunnels from harsh groundwater conditions.
Hello. Today I'd like to explain the main focus of our study, which looks at water leakage in multi-arc tunnels using thermodynamic principle. In simple terms, our research explored the relationship between two things. First, the objective function value J, which represent the total free energy in water rock system, and secondly, the reaction power, which tell us how active or intense the chemical reaction are between water and the surrounding rocks. Here's the main question. How does a change in the value of J affect the strength of water rock system? And how does this increase the risk of water leakage in tunnels? Our hypothesis is as J decreases, the reaction power increases. This means that the chemical reaction become more intense and spontaneous. This is especially a problem when groundwater is acidic or contain carbon dioxide, as this stronger reaction can break down the rocks and increase its porosity as well as create path for water to leak. So why does this matter? A lower J means that the system is trying harder to reach chemical balance, which causes more reaction. In tunnels, environment, this weaken the surrounding rocks and can damage the waterproofing, leading to leakage. By understanding how J affects the reaction power, we can better predict how leak might develop over time, and this can help engineer design tunnels that are more resistant to leakage and could last longer over time.
Let's move on to the results and conclusion part. So we'll be touching on to the topics of contributors and also the consequences of the leakage. So for the first contributor, it would be the carbon dioxide rich and also acidic groundwater that triggers the mineral reaction leads to leakage. So the groundwater taken as sample in this research has fixed data, which in our opinion doesn't reflect the real condition of the changing circumstances. So another one would be the grout, which in this research used the one that has carbon hydroxide, which means that if it used another type of grout, it would have react differently. So the third one would be moving into the consequences part. So these two previous reaction would lead to the increased rock permeability that will worsen the water flow. So in this model also, it has excluded mechanical effects such as cracking and also stress change. So these three combined would found the severe leakage in the approximately 1000 meter from the tunnel entrance, which in our opinion, it needs to be expanded and checks beyond the 1000 meter because only one location was validated here. Next up is the limitation and also suggestions. For the limitation, there's three basically. So the first one would be the model couldn't fully stimulate all the complex chemical reaction, and also this model also has violated basic chemical laws such as conservation of energy and also mass. And like previous studies, it used limited data and also has focused only on averages from a single run, which leads to my next suggestion, which is to use more diverse and repeated samples in future studies to better reflect on the real groundwater conditions. So next suggestion would be to improve the models to include more complex and also non-linear chemical behavior. And for the real tunnel project, which is to offer an solution for the problems the research has studied, which is for the real tunnel projects, is to enhance the waterproofing and also the drainage system. And last but not least is to use chemical grouting materials that resist acidic conditions.
The first area of focus that we want to highlight from this paper is time-dependent durability. From the positive side, the researcher limit the time frame to demonstrate the beginning of initial chemical reaction, and this can help and really realistically for modeling in early stage. The researcher can know the probability of leakage from the tunnel, and the engineer also can design the better waterproofing and also choose the chemical resistant material before the construction start.
For the negative part, researchers put an emphasis on the chemical and physical reaction between the tunnel lining and groundwater, but put the least attention on the corruption caused by this reaction over an extended period of time. The lifespan of the wall tunnel is between 15 to 100 years. So to achieve this, high-end material must be used, but the material used did not mention in the paper at all. So activities done by the people living near the bridge also contribute to the corruption. For example, the heavy ground stress caused by the transportation.
After that, the second area of focus that we can critique from this paper is the selection of the tunnel location. From the positive side, the researcher determined the fixed point and obtain the control and the simplified sample of the leakage. This is the critical structural zone which have a high pressure and the weight burden. So the result can be more mathematically trackable for the research.
A flaw was detected when the researcher took the length of the tunnel to be 100 meters from the entrance. The condition may vary from every part of the tunnel. For example, the stress distribution fluctuates whenever a car or any vehicle go through the tunnel. Also, the researcher may also overlook the fact that was caused by the corruption if they only took the small part of the tunnel.
Lastly, the element that we want to critique from this paper is the geometry of the wall. So from the broad side, the researcher select the double arc twin tunnel with a center partition wall, which are the actual and the real world design scenario. And most of the cases in China, the tunnel has been constructed in the loose and cast-prone area, which have the relation between the tunnel, acidic water, and also the hydrochemical interaction within the ground.
For the negative part, the detail on the shape and structural configuration of the tunnel was not mentioned, which weakened the comprehension of the study. Also, the clarification of the tunnel's shape was not found in this paper. The shape of the tunnel was significant because every shape act differently under different weights. Also, the joint positioning of each shape varies. It is hard to predict the leakage hotspot, which is significant for countermeasure.
In conclusion, while the study has limitation in scope and structural detail, it successfully highlights how chemical reactions, particularly with carbon dioxide and carbon hydroxide and organic matter, can lead to tunnel leakage in acidic groundwater. The use of Monte Carlo and thermodynamic modeling provides a solid foundation, but to ensure real-life world application, future research must focus on long-term durability and structural refinements. Despite its gaps, the study offers a meaningful step forward in internal waterproofing research and open doors for further engineering solutions and innovations.